Hello, everyone, and welcome. My name is Jessica Williams, and I am the Programs and Community Partnerships Manager at Chabot Space and Science Center. And we're thrilled to bring you another exciting program to your homes this evening. Thank you all for tuning in. Tonight we have with us Faride Khalaf, who will talk with us about the Perseverance rover, how it landed on Mars, and what it will do next. Before we get started, please consider making a donation to help us make these programs possible. These free events are fueled by our community, and thanks to you, we have been able to offer more than 75, probably more than 80 free STEM events since April. Right now, we need your help to create STEM learning opportunities for our community at home. In less than a minute, you can make a difference by donating on Facebook or at chabotspace.org. And we ask that you please take a second, click the button, and make an impact and support STEM education if you can. And now I would like to introduce to you Faride Khalaf. Faride is a retired career aviator with a passion for all things mechanical, and his lifelong love of science has driven him to studying and sharing the history of space exploration. He was an airplane pilot and also a longtime volunteer at Chabot Space and Science Center. Faride, thank you so much for joining us.
Hello, everyone. Thanks for having me tonight. Welcome, everyone, to the presentation. I'm still excited about last week's landing and 2 in a row for the Curiosity class rover. And with that, let's get started. Okay. How do I get to, I have to minimize this screen. What do I do?
Share screen.
Oh, okay, there you go. Share screen, and we're there.
Double click on this.
This?
Mm-hmm. Double click on this. There you go.
Okay, and then close that.
Uh-huh.
Okay, is everyone on board?
Looks great.
Sorry it took a minute. Okay, here we go. What I did is I recycled a presentation that I did before at Chabot back in 2013, I think it was. And I called it a stick landing, and I was just going to change this title to another stick landing. So those are 2 landings using the new technique with the descent crane using thrusters. And it's a really amazing feat. It's quite impressive. So let's start our program. With the Viking Lander, there were 2 of these robots sent to Mars, and they arrived in 1976. Vikings 1 and Viking 2, they landed, one landed in July of 76. The other one landed sometime, I think it was in September 3rd. I was an 8th grader in school, and I remember that event very well. My science teacher was really excited about it. And here's one of the pictures sent home back to Earth from Viking, one of the Vikings. And we can't call these rovers, so be careful. They have no wheels. They're like bar stools. When they won't move unless someone picks them up and moves them, and there's no one there to do that. And it is a color picture, even though you don't see a lot of rainbow in it. The American flag is a good test article for the color sensitivity of the film, and that is the true color of Mars. It's very rusty. But tonight, we're going to concentrate on what it takes to get there, and most importantly, the landing phase. But just to send a spacecraft to Mars, it takes about 9 months on a good launch window, on a favorable launch window, such as the one we just had, which delivered the Perseverance rover. Now, this is a little bit of an antique. Think of it as a 57 Chevy of a modern car, because this was launched in 1975. This is what a Viking spacecraft looked like in its cruise phase. And just from memory, it's similar to Curiosity and Perseverance, but the accompanying equipment's very different, but the aeroshell is similar, kind of like an egg, if you will. And eggs protect equipment that you put in them. They also, protect human body. Now, this is a shout out to one of my favorites, the late Robin Williams, who played Mork in Mork and Mindy. And Mork flew around and arrived from space to Earth in an egg. So this might be before your time if you're a millennial. And this is the Aeroshell of Viking, one of the Vikings, not sure which, but there were two of these sent. And you can see it has a kind of a compound conic shape, kind of cut in two angles, so to speak. And things don't look a whole lot different. Here's what the Curiosity rover shell looks like. It did look like that. It's all destroyed now because it was used in the delivery. And when Viking was sitting on the on the Martian surface, this is what it would look like. And that's the late, great Carl Sagan. Dr. Carl Sagan was a key player in these planetary probes that NASA and JPL sent into our solar system. And this is what it would look like if a person stood next to the latest iteration of our exploration abilities. We sent rovers now, and we've sent several of these. And I have the lineage here. This is at JPL's sandbox, so to speak. It's where the adults go to play with their toys, and you can see these toys are not cheap, and they're quite sophisticated. In 1997, we sent the Sojourner class, which was really a very tiny machine compared to some of the ones that followed. There's the Spirit and Opportunity rover chassis in 2004. And in 2012, we sent the latest and greatest with its very capable atomic energy source. It has a radioactive element called plutonium. It's a man-made element that's made in a nuclear reactor in power plants. And it's chemically taken out of the byproduct of modern nuclear electric generation. So the plutonium stays hot for a very long time. It has a long half-life and it gets very hot. And in that state, we take the heat from it, as you would geothermal energy, and turn it into electricity using thermocouples. And a thermocouple is a simple device. It's just two different types of metal that when they're bonded together real tight and exposed to heat, they produce electric current. And this is a tire size from the Sojourner all the way up to the Curiosity rover, to give you a scale. And there's the rover itself. The RTG, that's RTG, radioisotope. I knew there's an I in there. Radioisotope thermoelectric generator. It's a mouthful, and if you're familiar with aviation or space exploration, there are a lot of acronyms, and it's hard to keep track. And some of them are identical with different meanings. So it's a vast world of words and acronyms out there. So now we want to get this from Earth to Mars. How do we do that? We have to use Newton's second law of motion, where force times mass equals F equals ma, force equals mass times acceleration. So you take the mass of this spacecraft and get it moving real fast in the correct direction, and then you let it go. And by let it go, I mean you're done pushing it. So the propulsion phase ends with the long cruise phase that can take months. And when it arrives on the surface, the mission is really just getting started, but the delivery, which is a huge component, that portion is complete. So to get this thing in there into this tight little egg-shaped shell, this round shell, we have to make it so that it it's collapsible. So there's a lot of incredibly smart engineering that goes into making something like this compact. And then you send it out, and you can see in this picture the actual radioactive element is missing. If I can show it, it would be right there inside this cavity behind the rover. And of course, you're not going to put that in until you're ready to ship it, because it's not safe for people to be around plutonium, very dangerous. And then onto that aeroshell, the egg, you attach something like a service module. Basically, think of it as a trailer with all your food, water, electricity, communications, backup computers, anything, and thrusters. So there's all kinds of equipment that needs to go with the spacecraft for the long cruise. And that's what that cruise stage looks like. It's being lowered to the top of the the aeroshell here in the picture. Now, these like little teeth going around this top disc. The top disc faces Earth. It's got it. It's always looking at Earth and the sun, so that it can collect solar radiation and convert it into electricity using the photoelectric process, just like your solar panels on the roof, but much more efficient. These are the best you can get. And here are the technicians doing something. I'm not sure what he's doing. But these little panels I pointed out earlier, these are shields to protect the internal components. The things within it are being protected from galactic radiation. Not galactic, I mean cosmic radiation. The source isn't always a galaxy. It's other galaxies and other things that are in deep space, so far away, but we catch the radiation that comes from these events that happened a long time ago. So we have to protect the equipment from that. And that's the job of these curved shields. So think of them as a fence to guard against anything that might come in and do harm to these delicate components. And inside the aeroshell, you can see they have the rover stuffed in there, literally. And underneath, they close it off with the heat shield that's used for the entry into Mars' atmosphere. And you take this device that you've so far put together, and you're going to put this whole thing inside this aeroshell that's for the ascent phase as it's launched from your surface. It has to push through Earth's very thick atmosphere compared to Mars. We're 100 times thicker atmosphere around Earth. And you literally have to push the air out of the way so it doesn't crush this cargo. And that's the purpose of these shells, the clam shells. And they also protect from vibration, heat, and sound, and other inputs from launch. So I'm going to explain something here that's very important in just about everything. Even surfers have to do this. You shift your weight to steer your surfboard. You push on the nose, you go faster, you pull back. I'm not a surfer, I'm a body surfer, which is something I've tried, but I haven't tried surfing yet. And I live near Pismo Beach, which is kind of silly. Maybe someday. But here we have a simple scale, like a seesaw or a beam balance. And as long as it's perfectly level, it tells you that, basically the effects of both sides are equal. So they're going to be at the same level. Now, if one person moves away from the fulcrum, you're going to see that board tip. And so there are four things here. There's the weight of the people on both ends. There are two components. And then the other two components is their distance from the fulcrum. And that's called the moment arm. And the product of the two has to be equal. So 50 times 6 is 30, or whatever, 5 times 6. If you do the math, they're going to be equal. Now, these four quantities in this box, if you change any of those without changing something to keep the equality, you're going to get something that's going to change. So suddenly, let's say the guy empties his pockets. The adult dumps 20 pounds out of his pockets. He's got these gold nuggets and he empties his pockets. What's going to happen? The effect of the boy being heavier will be noticed because, you know, the adult's going to rise up. So this is an important concept because weight and balance is very important in controlling a spacecraft or anything that's in flight, an airplane, a rocket, or a projectile out of a gun, you know, like a 16-inch round out of a naval gun. It has to slowly spin to be stable. And that's how they stabilize those rounds. So I remember the first time I saw hang gliding and I heard of it, excuse me, I thought it was called hand gliding, as in handball. And until someone corrected me and said, no, it's hang gliding, like hanging something, like hanging your laundry on a line. And here's why they call it that. You can see the point where they hang everything from. By everything, I mean 2 very excited passengers. What a thrill of a ride that is. I used to skydive and I really miss it. And you can see in the background, someone else enjoying a different kind of flying. He's using a paraglider. But when you're hang gliding, your weight is hanging from the center of pressure of the craft that you're gliding on. And if you want to go to one side, you just pull that side toward you. So if you want to fly to the right, which would be our lift as we face the pilot, if you want to fly to his right, toward that other skydiver or parachutist, and you're going to pull that arm in. So by shifting your weight to that side, you bring that wing down and the aircraft moves in that direction. Now, if you pull the bar towards your feet, it's going to pull the nose down. You're going to pick up speed and descend rapidly. And if you want to climb, you push the bar forward, that lifts the nose. And all you're doing is you're shifting your weight. You're not doing anything else other than that. So weight positioning is very important in every aircraft and spacecraft. So center of mass, some people call it center of gravity, but center of gravity is also the center of mass. It's an inertial property of matter. And we can talk about that in detail on another topic. It's more physics. And here's another picture of the spacecraft about to be enclosed in a fairing on the tip of the rocket. Now you can see in this picture where I'm pointing 1, 2, 3, and then there are 3 others on the other side. These little dots are ballast. Think of those gold nuggets I mentioned, that if the adult emptied his pockets, the teeter-totter would go out of balance. Think of those as 6 chunks of gold that need to be jettisoned at some point to get that effect. It's a desirable effect at the right time, and I'll come back to that. And as we close it, you can see that we keep it sterile. The air that goes in there is pure nitrogen, filtered at the right temperature, moisture, everything. It's a very controlled environment. It's as clean a package as we've ever sent to Mars. Both rovers, the Curiosity MSL and the recent Perseverance. Now you lift it with a crane in the high bay and set it on top of a launch vehicle. In this case, it's the Atlas V with 4 strap-on solid boosters. They're right there. And the center stage is a kerosene and liquid oxygen fueled propulsion system with RD-180 engine, which is a very powerful engine built by the Russians, Energia. They have figured out the metallurgy to produce this type of engine, and we haven't figured it out. They're not going to tell us their secrets, so we buy from them. That's how it works. It's like the 11 herbs and spices. Okay, this is basically an exploded view of everything that's going to Mars. And you have to do a lot of math. I just threw that in there so you don't forget to do your homework for you young adults and children. Here's the launch vehicle at the moment of launch. And at the end of its burn of the first stage is still burning, but you can see the aeroshell is going to be split open. It's what I call parasitic weight. It's done its job of saving or protecting the payload from the Earth's atmosphere as we rapidly push through it on the ascent. And once we're in a clean environment of space, we can dump these shells, and then we can pick up more acceleration that way. And again, weight and balance. I'm going to remind you of that a few times. You can see those weights over here that I pointed out earlier. These are like tire weights on a wheel to keep everything balanced. Otherwise, you're going to get a kind of a shimmy in the steering wheel if it's in the front wheels, or a vibration in the rear, like a thumping noise, if your tires and wheels are out of balance. And I say tires and wheels. So think of this as a wheel and a tire assembly. There are two components here, like a tire and wheel. Both of these are rotating on their way to Mars at the rate of, I think it's one rotation every 2 minutes. And if Gerald's listening, he'll correct me either now or later. But anyway, I think it's once every 2 minutes. So 180 degrees of rotation per minute. And that gives it the same effect as a rifle bullet or a projectile from a naval gun slowly spinning. It gives you a stable flight. It also distributes thermal energy of heat through the spacecraft as it's received from the sun. So it kind of keeps everything even, kind of a rotisserie chicken mode. In fact, in the Apollo days, on their way to the moon, they had to do the same thing. Otherwise, one side of the spacecraft would be 250 degrees above zero and 250 degrees under zero on the other side. And you would literally bust some windows due to thermal expansion rates being different. So you have to keep it moving slowly. So the rotisserie mode is what they do. And if you don't have those tungsten ballast weights, this thing's going to wobble and not rotate clean on its own axis. And that makes it hard for the antennae to stay focused on the source and target of a radio station on Earth. It also reduces the efficiency of the solar panels because they're not always optimum positioned in an optimum way. So they wobble. That's not good. And here's a closer look. And this spacecraft in its shell is doing exactly what this baby is doing, taking a nap. There's nothing for it to do. So what do we have to do? Make sure it stays warm and doesn't catch cold overnight. Things don't freeze over. You remember from the movie Apollo 13, things can get cold real fast in space if you don't provide heating. So because they lost their oxygen tank and reduced electric load or electric production capacity, they had to endure some very cold temperatures. And those cold temperatures in space can actually do some harm to some of the equipment we're sending. So we have to control that environment. And we have to monitor the health of the baby on its way. And by baby, I mean this man's baby. One of the people who made this a possibility to land a 2,000-pound vehicle on Mars. None of the methods we used up to MSL would work. It was just too heavy. So we had to get inventive and create something completely new. And this is where Adam Steltzner came up with the idea. He's the architect of the crane descent, powered descent to Mars. And this sounded like a real outlandish way to go about it. But those of you who've been playing with these model airplane toys around, these rovers, that are doing amazing things. They have fireworks being replaced by a huge matrix of like a swarm of these rovers with LED lighting, working with a computer, and doing incredible stuff in the sky. It's technology never ceases to amaze me, and it's just exciting to see how far we can take this stuff. And here he's describing to his colleagues how this package is going to be delivered. And this is where people start scratching their heads and going, okay, is this really going to work? This is back then before it was proven. And here he is saying, yeah, this is what I think we should do. So if you've ever tried to sell an idea to an organization, some of you who've been around know what a challenge that can be. Just to get people to agree to do something a certain way is impressive, even on a small project. But think about this. Huge money on the line, taxpayer funded. You got the government breathing down your neck. Everybody's watching. Everyone's reporting on your progress. That's a lot of pressure for these scientists. Wow. I feel sweat coming down my forehead thinking about it. But here's a slide that shows the whole process. I'm just going to go through this real quick. You jettison this parasite device that you no longer need. And when I say parasite, at some stage, stuff becomes parasitic because, if it's lived out its usefulness and you don't need it anymore, then you don't need to carry it. And if you do carry it, you're carrying something for no reason. That's why I call it parasitic. It doesn't give you any benefit to carry it, so you get rid of it, assuming there's no harm in jettisoning it. And so then you're done with this cruise stage. And here it is, the cruise balance device separation. You can see those tungsten weights that are being released. And what that does is it throws the spacecraft out of balance. Remember those tire weights we talked about? We wanted them for the cruise stage, the cruising phase of the spacecraft while we're delivering the baby, but we don't want them there now that we've gotten close to the atmosphere. We want to get rid of them, and there's a reason for that. And then you interface with the atmosphere and decelerate rapidly, maximum pressure here. So if you're sitting in this thing at this point, that's the point of maximum aerodynamic pressure. It's the reverse of maximum dynamic pressure, or max Q, on a rocket that's lifting off of Earth's surface. You hear that in the description as they're narrating the event. They say max Q, or maximum point of maximum dynamic pressure. Well, you feel that going and coming into an atmosphere, and that's what you're feeling here. And it's not the same as the max temperatures and peak heating. That's more complicated to explain, so we'll just glide past that. And here you're in hypersonic flight, and you can see the spacecraft is tilted, and it's not on axis when it comes in, and then the parachute deploys and slows you down. You no longer need the heat shield, so you drop it. Just let it fall and crash into the surface. And the parachute slows you down, and the heat shield keeps going. And then at some point, you release the spacecraft, and it begins to descend under rocket power. And it really slows down fast under the thrusters. And then you lower it with a set of lanyards. And when it makes contact with the surface, you cut the lines from the spacecraft, and the crane flies away and crashes about 1.5 kilometers away. And it poses no threat or hazard to the spacecraft that you just delivered, the rover. Again, this takes a lot of math. That's why I threw this in there. Kids, I'm trying to kind of nudge you into loving and embracing math. You need to learn math to get there. And math is fun, and it's not hard. Don't let anybody tell you it's hard, okay? It isn't. It's easy. It's the easiest thing. Okay, so here we are about to enter the atmosphere. We want to do some thrusting to orient the shield so that it's facing the right angle. Otherwise, you can skip off the atmosphere. So you don't want to be, you want to come in kind of blunt. And you have your tire weights here, 6 of them. They use tungsten because tungsten is very dense, and it's denser than lead. We don't even use tire lead anymore. Here in California, they've outlawed it because lead is toxic and harmful to the environment as well. So we use tungsten instead. The benefit of tungsten over lead is also that it has a higher density. So you don't have to use as much by volume. So it can be compressed into a smaller package or smaller size. The dimensions give you the advantage. In fact, tungsten has a density very close to gold, and it's 11.9 grams per cubic centimeter, where lead is 11.3 grams per cubic centimeter. And to give you an idea how heavy that is, water per cubic centimeter is 1 gram. So lead is 11.3 times heavier than water for the same volume. And tungsten is 19.3 times heavier than water. So a bucket full of tungsten would be like 19.3 buckets of water. And that's how heavy this stuff is. And when you let it go, it just falls to the surface of Mars and it becomes junk. Now you're picking up a lot of heat here. And after you've done that, something I should mention, inside this, inside the heat shield, they embedded a ton of instruments. If I remember, they were called, not Molly. It starts with an M, Medley. Now that's an acronym for something, but Medley is basically the suite of instruments that measure the performance of the heat shield and also give you a whole bunch of other data that I couldn't possibly tell you about because I don't know everything that it did. But it was important to have this data because we're testing a whole new type of heat shield. It's much better than the ones we used in the Apollo days, Mercury and Gemini and Apollo. So we've had a chance to improve these heat shields so we can do faster interfaces with various atmospheres of places we plan to visit, like Mars and beyond, hopefully, and also coming home to Earth with our astronaut crews using the multi-purpose crew vehicle. So the information we get from this heat shield is helpful to a whole different class of spacecraft rated for human spaceflight. So just wanted to point that out. Everything you do on these spacecraft, if it's not for the mission itself, it's for something down the road in the future. You're always testing stuff. You always come up with answers to questions that you haven't even thought about. It's pretty amazing what they do. And now, again, weight and balance. I bring it up again because this is the point where you drop the gold nuggets out of your pocket. And if you become lighter on this side's going to drop. The side with the young boy is going to drop, right? And that's what you want. On this spacecraft, you want it to fall in foot heavy. Those are the 6 tungsten weights when they're being packaged. You can see them up close. They're just like little weights that you slide on the end of dumbbells and bench press with. Again, shifting your weight to one side makes the spacecraft fly in lopsided. You want it to go lopsided. You want it to be heavy on this corner. So it pushes in first. And you can see the axis of your travel, the aerodynamic direction, is different than this axis. The geometric axis that is the absolute center of this spacecraft, or the axis of the conic section. In other words, it's a symmetrical center. You would think you want the center of gravity there. No, but if you put it here, it causes it to fly tilted. And when it flies tilted, the air rushing past this side has to dip down. And it creates a little bit of a low pressure, partial vacuum. And it makes it so that the spacecraft flies in a curved path, much like a baseball. If you can throw a knuckleball, I don't know too many knuckleball throwers. I think at any one time, there might be 3 at the most in the entire league. in the American Baseball League. They can throw a knuckleball. It's a real skill to throw something without putting any kind of spin into it at high speed, because then it flies chaotically and erratically. But if you put a spin into it, then it flies in a stable, predictable path. And so by making our spacecraft come in lopsided, we create a pressure difference across the hull of the aircraft. You can call it an aircraft at this point because it's interfacing with the air. For all practical purposes, until it crashes or safely lands, it's an aircraft, okay? So that's how they did it in the Apollo program too. So let's back up here. Now, if I want to fly a different direction, all I have to do is use the thrusters to rotate on my axis, and then this thing will fly itself in a different curve. So you can actually steer which way you curve towards. And by doing that, you can actually steer to a landing target up ahead down here. And they did that with the Apollo program. And you could have quite a range. You can control where you land. You can actually make as much as a 60 nautical mile difference in your landing spot in range. That's impressive. Many people didn't know that, myself included, until I really started researching the Apollo program as an adult. But as a child, most adults around me didn't know any of this. We didn't have the internet. Believe me, we didn't have much. This was magic to us back then. And I'm dating myself. Yeah, I saw Apollo 11 landing live on TV. I was 7 years old. That's right. I was 7 years old. Here's the landing, the actual parachute they used on Mars Science Lab. It was tested in Mountain View, California, inside this huge wind tunnel. And last week, during the landing on the 18th, we had two guests from NASA, Shanna and, gosh, I think it was, I can't remember the other scientist that was with us, but one of them was in a photograph inside this very wind tunnel. It is a huge wind tunnel. They can fly a Boeing 737 inside it. Really, they can just fly it in there when it's blowing wind through it. It's that big. So here it's coming down on its parachutes. And here, the reason you want to get rid of that heat shield at some point is so that this suite of instruments begins to do its job. And that's the MALI, which is it's another acronym. It has to do with radar surveillance of the approaching ground that you're about to land on. So it maps the area and helps you land and select a spot for a safe landing. And this stuff, you can see the MALI instrument suite right here being, it's all covered up. Everything's covered until the last moment where they can, they want to keep it sterile before they install everything inside the aeroshell. And let's see, there's MALI right here. MALI had to be tested here on Earth, of course. So a lot of things we test here on Earth, we look for conditions that we can use to simulate things. So here they mounted the MALI instrument suite in just under the chin of a helicopter. It's a Eurocopter A350 that they leased from, or I think rent. They rented this from an outfit in Pasadena that flies out of Van Nuys. So it's a civilian helicopter that they rented, and Pasadena is where JPL is. So these guys have their local sourcing for this sort of thing. And they save a lot of money by not using military equipment, that sort of thing. And they're also simulating the exact distance below the MALI instrument suite, so they can simulate how they're going to land this thing so it doesn't land hard. You don't want to slam your cargo into the ground, and you don't want to drop it from the height. So all this stuff is being fine-tuned and tested. Again, I'm going to do this to you until you're seriously tired of it. Weight and balance. So if you're going to add all this stuff on the nose of the helicopter, you're going to have to do something to keep things balanced. So you add ballast at the right distance away from the center of lift. Otherwise, this aircraft would tip over on its nose and fly into the ground. It would never fly in the first place. That's how important weight and balance is. Okay, so Molly's busy looking and measuring. As we make our descent, you fire up these 8 rockets, and as it's dropped from its aeroshell and the parachute's gone, these wheels start to come out, and you have 8 nozzles pointed down to slow down its descent. Now, those 8 rockets fire together until they get really close to the ground, and only the ones that are canted away from the center line, in other words, they have divergent thrust paths in order to avoid blasting the hot gas on any part of the rover. You don't want to do damage. So you don't need the full thrust of 8 rockets to set it down. Now, some of the animations in the recent landing of Perseverance show all 8 thrusters going all the way to the ground. I would take that with a grain of salt. I would have to find out if that was in fact how they did it. I don't think they did, because the weight was similar. So there's no reason to do it differently. Those are little things you pick. You know, people who watch movies and look for little things that aren't real or fake. As an aviator, someone who worked on jetliners for a living, I love those movies because I just pick them apart. And some of them are actually really good, but most of them are not. Now, here's how good we've gotten at doing this. This is our expected landing area based on today's technology for Curiosity back in 2012. Now, look at how much leeway we had to have for Viking. The dartboard was huge, and we had a much smaller bullseye for Curiosity. That's because the technology is just so much better. We're really getting good at this stuff. And so good that these guys, of course, I really look up to them. Just they're inspirational. I wish I could live every experience that these guys had. It's just, and then of course, this is a big moment of pride for America. To get a lander on Mars with that kind of precision far outweighs anything we did technologically going to the moon. Yeah, we took people there and brought them home, but you know, that's easier to do than to get the kind of precision. The technology is just not even comparable, really. And there it is to this day doing its job. That's MSL Curiosity. And like every love story, you have to end on a slide, but this isn't the slide I want to end on. I want true love. None of this is possible if we didn't have love for math and science, okay? And with that, I went a little overtime, but sorry about that. I hope I was able to answer a lot of your questions just from the presentation, but I'm ready to be stumped. So let's have some questions.
That was great. Thank you so much, Faride. That was a really remarkable presentation. I love all the imagery, and it's just so fascinating to see how it's all done. We did have a couple questions coming in, and if you all have any more questions, feel free to put them in the chat on here on Facebook and on YouTube. So we're here waiting for your questions. One of the first questions that came in earlier regarding the spacecraft that took Perseverance to Mars, the shells that come off, does that become space junk or does that come back to Earth?
None of that stuff comes back to Earth. We wish it did because it would make great museum exhibits. It really would. And that stuff is really priceless. So I don't like to think of it as junk, but it is junk, really. It is space junk, but not the kind that's going to cause problems for us here on Earth, because the kind of space junk we typically bite our nails about is stuff in Earth orbit that can do harm to the spacecraft that we depend on for weather reports and national security, along with agriculture. Just about everything you can measure with a yardstick you can do from orbit. And we depend on the spacecraft for commerce and all kinds of stuff. So yeah, it's a space junk in a very safe location, and maybe someday we'll clean it up and bring it down to Earth and put it in a museum. That's a possibility.
Thank you. Another question is, why is the rover landing of Perseverance different than all of the others?
Perseverance isn't different from all of the others. It's different from, well, most of the others. There was one previous landing like it, and that was Curiosity. But this type of landing approach with the crane is different because to get a parachute to make a slow descent to landing, it would have to be really huge. That parachute really didn't slow it down nearly enough. The thin atmosphere of Mars with a parachute would give you some acceleration, negative acceleration, de-acceleration. In other words, it would slow you down quite a bit, but not enough for a safe landing. So if the package was smaller under a large parachute like that, it would still at some point need to cut away and use thrusters. But what they did for the rover, they didn't want the thrusters to be a part of the rover, because then it becomes parasitic junk attached like barnacles to a ship. They have no use anymore. So we want to make it space junk and not carry it with us. So how do we do it? We get rid of the parachute and then use thrusters for the very final phase. But because the thrusters had to be really powerful and it took a lot of fuel to do it, we didn't want any of that to be a part of the rover. So we separated that descent thruster element from the rover and separate them by cables and cut them so you can get rid of all that weight and put it a safe distance away. And now you have the lightweight instrument packed rover to do its job. It's sleek, it's clean, no barnacles. It's like the America's Cup versus the Bounty, which was a sailing ship back in the 1700s. Okay.
Great. We've got a couple more questions coming in. How were the sky crane cables cut?
Oh, those are easy. You can do it with a little guillotine. They can do pyrotechnics or spring-loaded guillotines. If you go on YouTube and look up some of those life rafts that they use on cruise ships, they use, in addition to the lifeboats that are lowered on davit cranes, they also have a whole bunch of self-inflating, encapsulated like a shell. They look like oil barrels and drums. And when the ship goes down, after several feet of depth, as it's sinking, the pressure changes inside of a little aneroid, and it releases a spring-loaded guillotine that cuts a cord to release the raft. And as the raft comes up, it yanks on a little ripcord that opens up a valve that inflates it. So it's all done automatically. So guillotines are real common. Guillotines were used for the separation of the ascent stage of the lunar lander, because all the cables that communicate between the two stages had to be severed to bring back the astronauts from Apollo. So also, if you're doing mid-air refueling, the Navy way, which is a drogue at the end of a hose that's spooled out, there are two ways to do that. There's the Air Force way with the boom operator that comes out with a solid boom and they fly it. The other way is the drogue and probe, which is what the Russians still use. They're really into using the probe. Now, what's good about that is if something should go wrong and the hose is stuck and they can't cut it off, they can guillotine that whole thing and just let it go. It's like cutting your fishing tackle, you know? So it's a little blade that chops it loose forcefully. It has to do it with one direct cut. So it's a very positive, clean cut.
Thank you.
Mm-hmm.
Few more coming in. Does orbiting space debris create launch problems?
Not so much launch problems, but it's more of a planning problem. You have to, select a proper orbit for the type of mission you're going to fly, and you're going to want to do this with minimal risk of collision with any of the space debris. Now, most space debris orbits in the same direction. So you not only want to go in a direction that's parallel flight path, you also want to space yourself. So it's a lot like air traffic control. So they control that. They actually know where everything larger than a centimeter is. Things smaller than that are hard to track, and everything's tracked with Earth-based radar. So space junk is a pain in the butt because you have to catalog it, you have to know where it is at all times, and you can predict close calls, and astronauts on the ISS from time to time have to, as a precaution, go to a safe location in the spacecraft because they know the approach angle and everything that's going to likely be the problem if there is a collision. So they take precautions, but the best thing is to avoid it. It's there. It's a hazard. So.
Yeah. Can you how combustion occurs in space during the ascent and descent phases without atmosphere?
Oh, that's an excellent question. Rockets are jet engines. Why do we call them jet engines? Why is it called Jet Propulsion Lab in Pasadena? My cup's not there. I was looking for my JPL coffee cup. Anyway, Jet Propulsion Lab, I used to ask myself that. They're not flying jet engines. They design rockets. Well, rockets are a type of jet engine. They call it a jet because it works on the principle of thrust produced from expulsion of a high velocity fluid. And if you expel a high velocity fluid, whether it's a gas or water, like on a jet ski or a jet boat, or on a jet airplane, you have a jet engine. And a jet engine can be a rocket engine if you take an atmosphere with it. What we take out of our atmosphere is the oxygen, and we burn it with fuel, fossil fuels, to produce thrust on a jet aircraft. But if you want a jet thruster in space, you have to take your oxygen with you. Think of it as a person breathing on the ground. You can go underwater if you take your breathing air with you in a tank. So rockets basically are jet engines that take breathing air with them. And so, yes, all rocket engines can function in space. And the way they do it is they're not dependent on an atmosphere. Like a scuba diver doesn't depend on the atmosphere. He depends on his tank having enough air for him to breathe. So that's the difference. Yeah.
Thank you. These are great. There's lots of questions coming in.
Oh, good. I'm here as long as you want me. So.
All right. How long does the nuclear powered battery last, and how fast can Perseverance travel across the surface?
Oh, good questions, both of those. One of them I'd have to look up the answer, but the half-life of plutonium is a very long period. I don't know how many years it is, but can you imagine something the size of a water bottle in your hand that is so hot, hundreds of degrees, and it's glowing red? That's what a chunk of plutonium looks like, just sitting there. It's happy being hot and producing a lot of heat. So all that heat becomes wasted, or you can use it. If you put thermocouples around it, you can create electricity. So the beauty of nuclear decay is that it takes such a long time. For example, a nuclear powered aircraft carrier can go 20 years without ever being fueled, where in World War II, the Hornet, which is a museum in Alameda, that's an aircraft carrier that burned fossil fuels. It had to receive full fuel every 3 to 4 days when it's in combat, and about every 12 days just on patrol. So nuclear energy can power you almost indefinitely. And since we're so far away from the sun on Mars, the solar energy we receive is very weak. So you need many, many times more surface area for solar cells to produce equivalent power. And it would take a long time to get a recharge. And so by charging their batteries overnight from a heat source that never goes quiet, never goes cold, for the duration of the mission, they can do that. That's why Voyagers 1 and 2 are still talking to us. They have the same energy source. Were it not for plutonium RTGs, we would never be able to leave our solar system because we wouldn't be able to fuel our equipment to communicate. So nuclear energy has its use. It's great stuff if you don't use it to hurt each other. So.
Wow, that's fascinating.
Yeah.
All right. Are the thrusters being controlled by an onboard computer or from JPL or NASA command centers?
All of this stuff is automated. No pilot has the skill to fly something like that onto the lunar surface, onto Mars. You really need automation. So computers do what humans can't do fast enough, and they do it quickly and accurately and dependably. They don't have any issue with fatigue, hunger, or anything. So yeah, you really need computers. Computers can do things the human mind's not fast enough to do. So in fact, before they were called computers, they were called sequencers on the Apollo program, because they do things in sequence, they do them quickly. Here's an example. When you do the countdown to liftoff on an Apollo moon rocket, the Saturn V, you would start the engines at T-6. You actually ignition sequence. You hear him say that. 8, 7, ignition sequence. 5, 4, 3, 2, 1. It takes 6 seconds for those engines to be checked out health-wise. If you had to do it by human hands, those engines would have to run for 3 hours before we could all talk to each other and say, yeah, my end's good, everything checks out. Okay, let it go. We can do that in seconds because we use sequencers to do 300 operations in 6 seconds. No team of humans can do that effectively. It's impossible. You would lose many rockets and you would give up. So sequencers became sophisticated computers, microprocessors, then computers. So they evolved, and you can enjoy this meeting because of that evolution. And we're lucky to have it. I can't wait to do this in person, people. Fingers crossed, get your vaccines.
Yes.
Next question.
Do you think Sky Crane will be how we will send initial human base components there before humans travel there?
Possibly. Anything's possible with that. You do have to send quite a bit of hardware there and some robots to sort of set up your camp for you. Think of them as roadies to build the stage, and here you are, the Rolling Stones. You show up and do your thing. And so the superstars, the rock stars, and astronauts arrive after you send a lot of robots to do that stuff. Everything's going to be automated, much of it. And the human portion of it is going to be the decision-making element that, no one can replace a human mind. I don't believe in artificial intelligence. I believe in real intelligence. And until artificial intelligence becomes real intelligence, I want to fly out of the pilot seat, not autopilot. There's a place for humans in space, no question about it. We want to get there so we can propagate the species and safeguard against any kind of astronomical event that might bring about extinction at some level to humanity, like the dinosaurs. So if we get a big enough comet collision, if we can preserve humanity abroad, by abroad I mean way out there in space, that's the dream. And if you want to really read about that, there's a good book called The Pale Blue Dot by Carl Sagan. Get the audio version. It has his haunting voice from beyond. And sit in front of the fireplace, kill 4 hours listening to that. It will blow your mind. It's beautiful. It really makes you think, and humbling thoughts too.
Wow.
Yeah.
Well, that actually kind of leads to the next question. Is JPL researching onboard engine technology that could decrease the travel time to Mars or other interplanetary destinations?
That's a lot of work, figuring out propulsion systems for the future, and for the near future as well. There's some companies working very independently from NASA hoping to corner that market and bring the technology into fruition. Oh gosh, there was a South American descent astronaut who flew 5 missions on the space shuttle. I want to say Diaz is his last name. I can't remember his name. He has a beautiful name too. And his lifelong dream as a child was to come to America and become an astronaut. So his father took him seriously and immigrated for that reason. And he went to MIT and he's studying. He finished his studies at MIT, joined NASA, did 5 space missions, and retired from NASA. And as a physicist and a PhD, he's developing the Vasimir engine, which is a very high velocity energy beam type engine where you use Newton's formula. It's classical mechanics, where you accelerate a mass to produce a great force for acceleration. But you're talking about particles, like atomic sized particles and subparticles, being accelerated magnetically out of a fine beam. What it does is it gives you very small thrust, but it can carry less fuel and give you that small thrust for a very long period. So for distant travel, it's a good application where you don't have to carry a barge full of fuel and then carry bigger engines so you can carry that barge full of fuel. It's a problem that snowballs. So when we come up with these, high-tech solutions, we're really learning how to get a bigger bang for the buck and do more with what we know. And the more we know, the more we can do. That's why science is so critical to our survival, literally. That's it for that one.
I'm reading. There's more.
Oh.
Pick and choose. We'll probably take like 2 more.
Okay.
Why is the launch window to Mars open every 26 months?
That's an excellent question. It has to do with the position in its orbit. And let's say this is the sun. This is a spray bottle, okay, for my plants. And let's say this is Earth and Mars is this finger. And if the sun's between us, we're pretty far apart. Take the orbit of Mars, the distance from Mars to the sun, and then add our distance on the other side, 97, what is it, 97 million miles, I think, is our distance, about 93 million miles, an astronomical unit, plus the orbital distance of Mars, which is greater than Earth's orbit. And so it takes a lot longer if we went there at that time. Why would we do that? We couldn't pull it off with what we have now, the equipment. We need to go to Mars when it's closest to us. So when it's in conjunction, meaning on the same side of the sun as we are, okay, if you can imagine that, then it's going to be closest to us. That's our launch window. But we don't launch at exact moment then. We launch 9 months ahead of time and do the math backwards or forwards and figure out how long it takes for these 2 planets to get to the right position. So the position in their orbits is what's important. And that launch window comes and goes every couple of years. And if you miss it, you have to wait for the next bus. There's no other way. That's why.
It's a long wait.
Yeah.
All right, 1 more. Does Perseverance transmit data faster to Earth than the earlier Mars probes?
Without even knowing the answer to that, I'm going to say yes, just because the technology is better. And that's an educated guess. And I could be wrong. That's always a possibility because I don't know for sure. But I would imagine so, because think of a Chevy Suburban that you bought last year, 2020 model. And you had one before it. It was a 2012 model. That was the previous Mars landing we did. Oh, they're different. Better GPS navigation, all the bells and whistles. It's a better ride. It's quieter. I don't know, cost a little more. But yeah, with evolution and time, there's going to be substantial improvements and advancements and features. So the data rate is going to be better, I think. Now, this is something I looked at. I don't think I can confirm this until I check with sources like NASA, Gerald, and other knowledgeable people who actually know the answer. But it looked to me, to my eyes, like the RTG on the recent Perseverance rover is a little bit different than Mars Science Lab Curiosity. Curiosity had these big cooling fins, like a CPU cooling heat sink. Those computer nerds out there who've looked at a motherboard, underneath the central processor unit, there's a heat sink that has, you know, fanning blades on it. It's aluminum. It gets rid of heat as the fan blows across it. That's a radiator. I didn't notice a radiator on Perseverance. It looked like it was enclosed without fins. And I think I know why. I think that they're trapping that waste heat and using it to keep some of the equipment in a safer environment by temperature control, environmental controls. So that wasted heat on Curiosity is probably being purposed to produce either more power, or it could be a longer RTG with an extra chunk of plutonium in it to produce more electricity with thermocouples. I don't know, but I'm guessing that the power demand for the mission that it's on is going to be greater, and that it would explain the larger RTG. So are they exactly the same? No, they look the same, much like a 747 that was built in the 70s. On the exterior, they look very similar to the ones recently built, but they are vastly different. Wing design, engines, so much is different. The landing gear, entertainment system. Remember the old entertainment systems in airplanes where it was a plastic tube with two little holes, you stick it in a seat, and it was literally an echo tube. And those things were horrible. I have some somewhere I kept. So anyway, in my antique collection. Yeah, the technology evolves really fast. In fact, I'm sure what they sent to Mars this time around, there was a lot of afterthoughts from the first one that they said, oh, we should have sent this. We should have put one of these on next time. And so those get carried over, plus more equipment, more ideas. NASA, if you want to drown yourself in brilliance and ideas and thoughts, you have to work for a place like that, where you're just immersed in pure science and thought. And it just going on tours of these places just tickles me. I love NASA. So the NASA and the post office, the best government agencies we've got, they do so much good for us. Deliver things. So keep up your support for NASA and science and STEM and education. And I think that was our last question for tonight.
Yes, I wish we had some more time, but thank you for so much.
We'll do it again.
Fascinating talk. I know that our audience is loving it as well. Lots of great questions coming in, and yeah, just thank you so much. We learned so much tonight, and it was just so great to hear, you know, some extra details about the launch and look a little bit closer at what was going on. So
visit NASA's websites, and you will. It's like a book you can't put down, and just go for it. Read and explore NASA's websites. I don't know why people don't get stuck on those. You know, I mean, that's a go-to for me. I love it. Never get tired of their websites and their knowledge. And it's all paid for by your tax dollars, and you own it. So you don't have to worry about, is it okay to learn this stuff? No, everything on there is not classified if it's on their webpage, and it's for your benefit. And if you use any of their photos, they just ask for credit, not money. So just, you know, whoever you share it with, tell them where you got it. So it bodes well for them and keeps them funded and alive. So. Yeah.
That's great. Well, thank you so much, Faride, again for the talk, and thank you all for tuning in tonight as well. We hope that you'll join us again tomorrow night for our virtual telescope viewing with Gerald and Richard and team, and we'll be on at 9 p.m. Hopefully, weather permitting. We'll have some good viewing tomorrow night so we can look at the sky through the telescopes. And thank you all for everyone who donated this evening as well, and thanks to you, we're able to keep these programs going. And if you're interested and continuing to help us with your donations. We have a donate button here on Facebook, or you can go to our website at chabospace.org. And every donation helps with creating STEM learning opportunities for our community at home during this time while we're closed. So thank you all for joining us, and we'll look forward to seeing you again next time. Good evening. Thank you, Faride.
Bye. Thanks.